Hi everyone. Today we'll take a look at another example of permutation combinations which involves circular permutation. So the circular permutation in which clockwise and the anti-clockwise arrangements kind of give rise to a different permutations, okay? And I'll tell you why this is important. Okay, so let's take an example, okay? Let's take an example. And our example includes seating arrangements of people around the table, okay? Seating arrangements of people around the table, okay? So essentially, if you just want to memorize it, right? Let's say I have a table, round table, and I have 1, 2, 3, 4, 5, 6 slots, okay? And I want to figure out how many ways I can, arrange them. So if you just want to memorize it, I'll just give the formula. The number of ways in which, n number of people, right? For n people, right? It's gonna be n minus 1 factorial ways. Okay? N minus 1 factorial ways. Okay, so now why is this, right? That's important to understand now. Okay, so let's say there are 6 slots here. Okay, so slot, let's call it A, B, C, D, E, and F. Okay, let's say, ideally if I had, a whole line, right, of 1, 2, 3, 4, 5, 6, I would call it 6 factorial and get it over with, right? That's the most logical way of starting. Fair enough. However, I can't do the same for circular arrangements, because let's say if I allocated seat A, seat B, seat C, seat D, seat E, and seat F to the respective people, okay? But what if I rotated the table clockwise once? What's going to happen then? Well, the arrangement's still the same. I mean, the direction's a little different. I mean, the direction's going to be kind of, like F, A, B, C, D, and E. But if you notice, on the left of A is F, on the right of A is B, right? So essentially, to do any sort of these calculations or these questions, what we really have to do is we have to lock a position. So let's say in this case I lock person A, okay? I'm gonna fix this person to stay here only. It's not gonna change. So once I lock or affix a position to a respective person, then I can do my permutations the same way I would do it if they were in one single row. So if I lock this, how many other positions are available? Okay, 5 positions. Therefore, I have for n people, I'm going to have n minus 1, which is 5 factorial ways. I hope that makes sense. I mean, there's nothing much to it. It's just, this is the idea. I mean, you can simplify it with 3 people as well if you want. You can take up 3 cases. So let's say you have A, B, C in a round table like this. And then you can maybe have, A and B and C, kind of like this in a round table. I mean, this is the most you can have. Because if you do B, A, and C, well, these two are the same exact thing. They're just rotated each position clockwise once, right? That's it. Besides that, everything else is the same. Okay? Alright, so the circular permutations in which clockwise and the anti-clockwise arrangements give rise to different permutations. Example. So the number of ways in which n persons or n people can be seated around the table is n minus 1. Again, seating arrangement of people around the table, right? So same thing, that just what I iterated, I've put it up here. There's nothing much more to it. Okay. Alright, so now the circular permutations which clockwise and anti-clockwise arrangements give the same permutations. Okay, now when can this happen? Right, arranging some beads to form a necklace, for example. Okay, in this situation, what we do is we take n minus 1 whole factorial, but we just divide it by 2 because they are basically mirroring. Okay, so If I had to show an example, maybe let's say we do blue. We're making a bead of a bead, okay, necklace bead. We have blue, green, and blue, green. Okay, so now if we go clockwise or anti-clockwise, it's essentially the same thing, right? It's the same arrangement. That's why I'm dividing it by 2. But in the previous slide, right, we just keep it as n minus 1 factorial because clockwise and anti-clockwise arrangements give different permutations. Okay, different permutations. So that includes people, that includes any sort of things which can be distinguished from another. Okay. Okay, so let's have a look at this example. So we're given 3 cases and we have 5 boys and 4 girls are sitting on a circular table. Okay, so in the first case, we're asked to find the number of ways they can be arranged such that no 2 girls are together. Okay, so let's draw a big table. Okay, let's draw a big circular table. Okay, let's place 5 boys. Okay, so we have boy 1, boy 2, boy 3, boy 4, and boy 5. Okay, I'll just create some squares around them. Okay, like this. Perfect. Okay, so now we have 1 slot, 2 slot, 3, 4, and 5 slots where the girls can be placed. So before that, let's find the number of ways the boys can be arranged. Well, simple working for that, we'll just have 5 minus 1 whole factorial, right? Just n minus 1 factorial ways the boys can be arranged. Now for the girls, well, we have 5 options where we can place the 4 of them, right? So we're going to do 5C4. 5 ways, and we're choosing the 4 slots because it doesn't really matter where they're being placed as long as they're being placed. Now, there's still one more thing we got to add. Now that we have, let's say I chose this slot, this slot, this slot, and this slot, okay? Now we have to arrange them in these slots, okay? To arrange them in these slots, I'm going to have to do 4 factorial, okay? 4 factorial, okay? Now, the reason why I'm doing 4 factorial and not 3 factorial, there's a reason for that, okay? So these boys are already fixed, okay? And let's say I've chosen these 4 slots for the girls, okay? For now, I could have chosen this one as well, but I didn't, okay? So now these, I can treat these arrows that I've marked as a line, you can say, okay? Now these 4 arrows are no more a circular arrangement. They're kind of like a line. If you look at them, it's kind of like a line that's going like this, okay? Let me change the color. They're kind of like a line that I'm just placing like this, that's going like this, okay? So that is why I'm doing 4 factorial, not 3 factorial, okay? Now let's simplify this a little bit, and I'm not going to write the final answer, but you can kind of figure it out. 5 factorial, 5C4 is 5, and we have 4 factorial. And now 4 factorial times 5 is just 5 factorial, or no, sorry, this is 4 factorial, I'm so sorry. Hold up, so this is 4 factorial, so we have 5 factorial times 4 factorial. Okay, that's our final answer. Now let's look at the second case where all girls are together. So for all girls to be together, let's treat them as one big group. Okay, so before that, let me draw a nice big circle like this. Okay, I'm gonna do let me change the color. I'll take red. I'll do G1, G2, G3, G4. Okay, and I'll block them up like this. Okay, like this. Okay, now I'm gonna have boy 1, boy 2, boy 3, boy 4, and boy 5. Okay, so now what do we do? Now I'm gonna treat this as one entire entity. Remember, that's what I did in the previous permutations videos as well. I think I've done it bundling, I've done it separating in that one for sure. Okay, so if I treat this as one complete entity, I have 1, 2, 3, 4, 5, 6. Okay, so I have 6 minus 1 factorial ways they can be arranged. However, since this is a whole bundle, right? I've bundled this up, the girls together. I can arrange these girls in 4 factorial ways. Again, I'm not going to do 4 minus 1 because there's no circular arrangement for this. It's just a linear arrangement, okay? So my final answer is going to be 5 factorial times 4 factorial. This was case 2, okay? Case 3, we have all girls G1 and G2 sit together, but not adjacent to G3. So this is a little tricky situation. However, we can break it down, okay? So we have case 3, okay? And we have boy 1, boy 2, boy 3, boy 4, boy 5, along with G1, G2, G3, and G4, okay? Now, we're told that girls G1 and G2 sit together, but not adjacent to G3, okay? Maybe they have some beef, okay? So let's block them up together because they're going to sit together, okay? And these two cannot be together. Alright, so like always, what I'm going to do is this time I'm going to make arrangement with all the boys and girl 4 because she doesn't have any problem, so she can sit with anyone, okay? Let's make a table like this, okay? And then I'll write them out. So I'll have boy 1, boy 2, boy 3, boy 4, boy 5, and I'll have my G4, okay? Now I can fit G1, G2 as one entity anywhere, but just they should be, you know, they have to be in these slots, okay? They have to be in these slots, okay? So 1, 2, 3, 4, 5, 6, okay? That's about it. So again, let's do the arrangement for everything in red. So that includes all the boys and girl 4, okay? So that's going to give me 6, right? 6 minus 1 factorial. 6 minus 1 factorial, okay? Now, there are, how many slots are there? 1, 2, 3, 4, 5, 6. So there are 6 slots, okay? There are 6 slots and 2 groups which I have to put. So I can place them in 6C2 ways, okay? 6C2 ways. Again, same approach as the previous question, okay? Nothing's changing, okay? Now, let's say I have chosen this one and this one, okay? Where I'm going to place these two groups, okay? First group is with G1 and G2. Second group is just with G3, okay? Now, these two groups can also be arranged in 2 factorial ways. Remember, now it's a linear arrangement because I just have this slot and this slot. It's not a circular arrangement. So it's not going to be 2 minus 1 whole factorial. It's just going to be 2 factorial. Then we have our final group. Now remember, this is a bundle. So again, there's a linear arrangement within this bundle itself, which can be arranged, you got that right, 2 factorial ways. Okay? Again, this is a little annoying of a question, but I hope the approach is the same every time. Okay? So let's simplify this. We have 5 factorial, we have 6 factorial, by 4 factorial, by 2 factorial, times 2 factorial, times 2 factorial, okay? So this cancels off, okay? This is going to cancel off. 6 times 5 is 30, okay? And this should give us a solid, 10 times 6 factorial, okay? That should be some number, but that doesn't really matter. That's not the point of this question anyways. Okay, so I hope this kind of explained of the various different arrangements that can be asked of you. Okay, now we have a beads question. Okay, so remember, for the beads question we just divide everything by 2. Okay, so we're asked how many different necklaces can be made from 10 different beads such that 3 particular beads always come together. Okay, 3 particular beads always come together. Now, again, why am I dividing by 2 even if this is different? Okay, chances of such questions in the IB are pretty slim, but I just brought this concept just to add depth to the entire topic. So the idea is, if I take a bead, right, if I have, let's say 7 beads of Roy G. Biff, okay, Roy Biff, okay, whether I keep them like this or like this, I mean, at the end of the day, it's the same thing, right? If I'm gonna have red, orange, yellow, green, blue, indigo, violet, or if I start with violet, indigo, blue, green, yellow, orange, red, it's the same thing. Like, it really doesn't matter because it's not a person, it's not some different flavors of ice cream or something like that. It really has no essence to it. That's why I'm dividing it by 2. Anyways, such questions coming in the IB are pretty slim, but it's something I think it's interesting to share. Anyways, so how many ways can they be arranged? 10 different beads be arranged such that 3 particular beads are always together. Okay, so let's draw it out. Okay, let's draw it out. So I have a big table or a big string, and I'm gonna put beads around it. Okay, so I have bead 1, bead 2, bead 3, bead 4, bead 5, bead 6, bead 7, bead 8, bead 9, bead 10. Okay, now let's say 8, 9, and 10 are the ones that are being grouped together. Okay, like this. So here we have our group, and how do we simplify? How do we work? Okay, so first, let's say this is group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. So we have 8 different groups. Similarly, we're just going to do 8 minus 1 whole factorial by 2. Okay, that's it. That's our basic working, because we have 8 different entities or 8 different groups, and these within 8, 9, 10 can be arranged a grand total of 3 factorial ways, right? So that's it. That's literally it. There's going to be a linear arrangement. There's no circular arrangement within the groups, because remember, it's just in a linear form. So what do we have? We have 7 factorial by times 3. Sorry, that's our answer. Super simple, nothing too crazy. Okay, next question. So we're asked if 7 women, okay, if 7 women and 7 men are to be seated around a circular table such that there is a man on every side of every woman, then the number of seating arrangements is 1. Again, super simple question. I think you should pause the video and give this a shot on your own. Okay, so let's draw the table. Okay, so we're going to draw a table, and we're gonna let's allocate the men. Okay, first. So we have M1, M2, M3, M4, M5, M6, and M7. Okay, so how many ways can the men be arranged? Well, that's pretty obvious. 7 minus 1 whole factorial, right? Now again, how many slots do we have for the women? Well, we have 1, 2, 3, 4, 5, 6, and 7. And how many women are there? Well, there are 7 women. So I'll take yellow. I'll take 7C7. Okay, that's basically 1. And how many ways can these women be arranged? Well, that's 7 factorial ways. 7 factorial ways. Again, I've taken 7 because think of it as a linear arrangement. If I start filling it up here, let's say I do woman 1 here, woman 2, woman 3, woman 4, woman 5, woman 6, woman 7, right? Now if I rotate them all the way to the clockwise ones, what am I gonna have then? Well, I'm gonna have woman 7, woman 1, woman 2, woman 3, woman 4, woman 5, and woman 6. And yes, it matters if I change it up, because why? The men are already fixed in one place, right? I've already fixed the orientation by doing 7 minus 1. So let's say if I have M1, all the reds, all the men are sitting in the same position. If women rotate once, yes, the number of ways is going to increase. It's not going to be the same. It's not going to be redundant, right? So that's why it's 7 factorial. I could have done it the other way around. I could have placed the women first, then done 7 minus 1 factorial, then done it for the men, 7C7, and then 7 factorial. I would have got the same thing, yes. So yeah, that's the idea. That's why I'm putting 7 factorial and I'm not putting 7 minus 1 whole factorial. So let's just simplify this out. We have 6 factorial times 7 factorial. That's it. Okay, so now the next question, we have the number of ways in which 5 boys, 3 girls can be seated on a round table if a particular boy B1 and a particular girl, G1, never sit adjacent to each other. Okay. So let's do it out. Okay, let's list it out. Okay, so we have let's list the boys out: B1, B2, B3, B4, and B5, and we have 3 girls. So G1, G2, G3. Okay. Now, boy 1 and girl 1 can never be together. Okay, so rest of the other people have no problems. Okay, so I'm gonna make a table and I'm gonna arrange all the boys and all B2, B3, B4, B5, and G2 and G3 all together. Okay, so I have one big circle. Okay, and I'm gonna have B2, B3, B4, B5, G2, and G3. Okay, what are the slots for the boy 1 and girl 1? Well, that's 1, 2, 3, 4, 5, 6. Okay, one important thing I forgot to mention is that, let's say you have multiple groups like this, right? Let's say this is let me change the color. Let's say this is one group, right? And this is another group, the one that's not in the blue circle. Well, you should always first write out the group which has more people, because if that has more people, it's going to have more slots in between, and then you're going to get the more correct answer. Because if you're going to put out boy 1 and girl 1, well, there's going to be a lot of empty space between them, right? So it's not going to come out to be the right answer. Always list out the people or the group which has more elements in it. Okay, so how many ways can all the people in blue be arranged? Well, that's 1, 2, 3, 4, 5, 6. So 6 minus 1 factorial ways. So 6 minus 1 factorial, right? Right? And there are 6 slots, 1, 2, 3, 4, 5, 6. And there are 2 people, right? 6C2, right? 6C2 ways. And how many ways? Let's say I take, let me take red, okay? Let's say I fix this slot and this slot, okay? How many ways can they be arranged? Well, that's 2 factorial ways, right? Because it's a linear arrangement now. It doesn't matter. Okay, so again, super simple question. I'll just simplify it a little bit. I don't really need to, but I'll still do it. 5 factorial times 6 factorial times 2 factorial times 4 factorial and 2 factorial again. So this cancels off with this. 5 factorial by 4 factorial is just 5. So I'm left with 6 factorial times 5. That's it. Okay, that's my final answer. Alright, so next question we have 8 people, including A and B, are to be seated around 2 identical tables, each having a capacity of 4. The number of seating arrangements that A and B are not on the same table is what? Okay, so if they're not on the same table, okay, so let me draw 2 tables first. 1, 2, and let's say that if this is on, if a person A is in here, we have 3 empty slots, and B is here, again 3 empty slots, right? So we have 6 empty slots. Now what's going to be the answer? Is it going to be 3 factorial times 3 factorial? Is it going to be 2 factorial times 2 factorial? Or is it going to be 6 factorial? Well, I'll tell you the answer first, then I'm going to reason through it. Okay, so the answer is going to be 6 factorial ways. Okay, why? Because we have 6, 1, 2, 3, 4, 5, 6 empty slots. Now I'll tell you why. If you remember, the first condition of doing any sort of circular arrangements is we have to fix a person in a particular position. In this question, we have fixed person A in the first table and person B in the second table. So our criteria of fixing is over. Now it's just whatever the number of empty slots are, we just do that factorial ways, right? Here, we don't do 3 factorial times 3 factorial. No, we don't need to. We treat this as like a linear operation. Think of this as, if we have slot 1, space 2, space 3, space 4, space 5, space 6 as, 6, separate spaces where we can place the remaining 6 people. We don't care. It really doesn't matter. Again, it's something that's really difficult to come by intuitively, but I hope it makes sense. And you just have to keep doing such questions till you actually get a hang of it. Okay, so this is basically 720 ways. Okay, again, whole criteria of circular arrangement is just to fix people first. Once you have fixed them, then it's just a game of doing the number of empty spaces and the factorial. Okay, so in this next question we have 8 people are to be seated, including A and B. So now we have to find the number of arrangements in which A and B are not at the round table. Okay, if they're not at the round table, well, that means they're at the straight table, right? Straight table. Okay, so let's list out the straight table. 1, 2, 3, 4, and we have a round table. Okay, so in the round table we have 1, 2, 3, 4. Okay, so let's say this is A, this is B, right? They're somewhere around in this location. We don't really care. How do we do this? Okay, how exactly do we do this? Well, for starters, there are going to be 4 random people. Let's say E, F, G, H, right? So that's going to be 4 minus 1 factorial, which is 3 factorial. Okay, that's done. That's easy. Okay. Now, we know for a fact that there are a total of 6 people who are supposed to be allocated in these slots, right? Okay, there's supposed to be 6 people who are supposed to be allocated in these 2 slots. Okay, essentially, right? Because we know that 2 of them are going to be taken by A and B. So, how many people can come in this? Well, that's 6C2, right? So 6C2 is the ways this can be arranged, because 2 are already taken by A and B. I'm just putting these 2 arbitrarily right now, but we haven't arranged them. We've just selected them right now. So we have 6C2 ways times 4 factorial by default, because we're gonna have to arrange these people in 4 factorial ways. Now that leaves us with 3 factorial ways for the round table, right? I hope that makes sense. That's what I've done, right? Obviously there's gonna be 3 factorial ways regardless. That's why I did it first, because that's the easy one to do. Okay, so that's what the 2 comes because we only have 2 slots, because A and B have already taken up 2. That remains 2 empty slots where I can put in 6 people. So 6C2 times 4 factorial, because they can be arranged 4 factorial ways, and the circular permutation. This gives me a grand total of, I think, 6 factorial times 3 factorial ways. Okay, that's it. That's my answer. Alright, so with this we can wrap up circular permutations or circular arrangements. I hope this made a lot more sense, because this is it's quite common all across within the permutations and combinations chapter, and it's something you should mostly be aware of. So I thought it's important to get a lot of different questions that make a lot of sense. And yeah, that's about it for circular arrangements, and I'll see you in the next one. Bye bye.